There's a wall in the universe you can't photograph. It's not made of stone or dust. It exists because physics throttles every observation we attempt. Bottom line right away, light, noise, and geometry cap our view. Picture a camera staring into perfect darkness, hunting a whisper. That camera still hits limits, even if money is infinite. Waves blur, photons arrive randomly, and the cosmos has horizons. No single trick beats all three at once. We can push them back, but never delete them. Today we'll map those limits, then show how astronomers squeeze past edges, so you'll see where impossible actually begins. You stand beside a giant mirror under a cold sky. The metal sings softly as the night cools. Stars look sharp, but physics draws a line. Diffraction sets the smallest separable angle for any telescope. That angle decides if 2 points smear into one. Bigger mirrors shrink it, smaller mirrors grow it. The simple relation is wavelength divided by diameter times a constant. That constant is about 1.22. Waves curl around the aperture edge, then interfere into rings. The central spot is the airy disk, which defines detail. Rule of thumb, shorter wavelengths and larger diameters resolve more. At 500 nanometers, a 6.5-meter mirror resolves beautifully. You get about 0.02 arcseconds on the sky. That can split stars the eye blends together as one. Shift to radio and the game flips completely. At 21 centimeters, even 100 meters looks blurry. The same formula yields many arc minutes of fuzz. Interferometers connect dishes, synthesizing a gigantic virtual mirror. Baselines hundreds to thousands of kilometers carve micro-arcsecond vision. That is how the Event Horizon Telescope sees shadows. Resolution, however, is useless without enough photons arriving. Photons land randomly, so your signal has shot noise. Collect n photons and the noise scales as square root n. Double the exposure and you gain only modest confidence. Squeeze more area and you count photons faster. Cool the detectors and you lower added noise. Everything funnels toward one trade, blur versus certainty. We chase both, but physics never gives both completely. So resolution and photon statistics set our first hard boundary. Lasers spear the sky above a mountain observatory at dusk. The beams look like neon spears, steady yet alive. The air is not steady though, it is boiling. Turbulent cells bend starlight, then smear every sharp point. This blurring is called seeing, and it ruins detail. From typical ground sights, stars swell to 1 arcsecond. That overwhelms even a giant mirror's diffraction gift. Enter adaptive optics, a fast mirror that unwarps wavefronts. A bright star or laser guide star measures the distortions. Computers drive a deformable mirror hundreds of times each second. The mirror wrinkles, then flattens, canceling the air's mischief. Coherent patches in the air stay small and brief. Their size is called R0, usually inches wide. Their lifetime is milliseconds, so speed matters desperately. In good infrared bands, adaptive optics reaches near diffraction limits. 10-meter telescopes can hit around 0.03 arcseconds. That pulls planets from the glare of their stars. Short visible exposures, stacked carefully, can also beat averages. People call that lucky imaging, and it helps. Still, clouds, wind, and jet streams set shifting ceilings. Space removes the air entirely, and stability blooms. Hubble proved this with steady, crisp, reliable clarity. JWST extends it in the infrared with even colder optics. One-sentence recap: the atmosphere blurs pictures unless you cancel it fast. Now picture a faint galaxy drowning in a pale glow. The glow is not the galaxy, it is the sky. Even great telescopes see a background that never vanishes. Air molecules glow, aurora dances, and human lights leak upward. A dust haze near the sun scatters sunlight across space. That haze is zodiacal light, a bright veil in darkness. Telescopes themselves also radiate heat in the infrared. Warm optics spray unwanted photons into the detector. Those extra photons add noise, which smothers faint signals. Because noise from backgrounds follows square root behavior, patience struggles. Double time only yields a small improvement in contrast. Astronomers fight by leaving Earth and cooling their optics. At very dry sites, water vapor drops and windows open. Some wavelengths still slam into walls set by nature. The atmosphere blocks ultraviolet, far infrared, and much submillimeter radiation. In radio bands, human transmitters raise the noise floor. Good observatories hide in regulated quiet zones and deserts. Numbers help here. Darkness has a measurable surface brightness. A pristine site shows about 22 magnitudes per square arcsecond. A city can be 4 magnitudes brighter per unit area. That is 40 times more background light per patch. Space telescopes skip the air glow, which helps enormously. JWST keeps instruments near 40 Kelvin, suppressing thermal fog. Example in real terms, deep fields stack for days. That climbs to magnitude 30 for point sources in space. Bottom line, background glow sets a floor you must beat. Deep fields look like static, speckled with distant smudges. Many of those smudges are entire galaxies, shockingly far. They fade not only because they are distant, they fade per unit area due to cosmic expansion. Astronomers call this Tolman surface brightness dimming, and it bites hard. The rule is simple: brightness per area scales as 1 over 1 plus z to the fourth. Why care? Because it hides structure inside early galaxies. Clumps that would be visible nearby flatten into gray haze. Photons also redshift, shifting color and energy to longer wavelengths. Arrival rates stretch too, so fewer hit your detector each second. The galaxy's apparent size changes, which complicates interpretation. K-corrections then punish observations in the wrong bandpass. Put numbers on it, pick a redshift of 6. That gives a dimming factor near 2,400. The same galaxy patch would look that many times fainter. JWST helps because it hunts red light efficiently. Infrared cameras catch light shifted from ultraviolet star factories. Strong lenses sometimes boost tiny regions enough for detail, but the overall haze keeps swallowing fine structure at high redshift. Astronomers stack images, model profiles, and share information across bands. They recover pieces, not the whole, past certain depths. Net result: expansion drains surface brightness faster than patience can chase. Crowded skies create a different, stubborn limit called confusion. Imagine every beam on the sky holding many sources. When that happens, their signals pile into one blended measurement. You cannot tell what light belongs to which object. This gets worse when the beam is large or crowded. The average number of sources per beam governs the pain. Past a threshold, the noise stops shrinking with time. More exposure only refines a blended, not isolated measurement. Submillimeter and far infrared surveys hit this wall quickly. Their beams are big compared with the galaxy density. People beat it with sharper beams or clever deblending. Priors from sharper images guide how to share the flux. Another tactic borrows nature's lens, gravity from massive clusters. A cluster can magnify a background galaxy by 10. It stretches and brightens a tiny patch into visibility. That trick helps, but it does not change confusion. You magnify the image and also the background area. The floor may move, but it rarely disappears entirely. Concrete example: Herschel surveys met confusion near a few millijanskis. Push harder and you still count blended galaxies together. Radio surveys meet a similar floor when beams stay broad. Very long baselines collapse that beam, which reduces confusion greatly. Optical deblending keeps improving with machine learning and priors. Gains are real, but the limit lurks underneath. So the picture is: crowded beams flatten depth into a floor. A compact radio source can look like a fuzzy balloon. The source itself is tiny, but the air is tricky. Turbulence in plasma between stars scatters radio waves. Many paths reach you with different delays and angles. The image looks broadened and pulses smear into tails. This is interstellar scattering, and it gets worse longer. The broadening often scales roughly as wavelength squared, so drop to longer wavelengths and detail collapses quickly. Aim toward the galactic center, and scattering dominates quickly. Sagittarius A star looked huge at gigahertz frequencies for decades. The apparent size at 1 gigahertz is about an arcsecond. That is an enormous halo around a tiny black hole. The Event Horizon Telescope dodges this by using short wavelengths. At 1.3 millimeters, scattering is much weaker. They also model the residual blur, then subtract. Pulsars feel this worse because their signals are sharp. Millisecond pulses can stretch, then vanish into the background. Observers pick cleaner lines of sight and higher frequencies. Interstellar gas also absorbs soft X-rays strongly. That hides hot regions behind curtains of atoms and dust, so transparency depends on wavelength and what sits in between. Rule of thumb: every band has a different fog. Bottom line: intervening plasma and atoms redraw your map of detail. Now zoom all the way out to the cosmic shell. There is a furthest light we can ever photograph. It wraps us as a sphere of ancient microwave glow. That glow is the cosmic microwave background, a baby picture. Before that time, the universe was a foggy plasma. Photons bounced constantly, unable to travel cleanly between charges. Then the universe cooled, atoms formed, and space turned transparent. We see that last scattering surface at redshift about 1100. Beyond it, light cannot carry an earlier electromagnetic picture. Two other messengers can, neutrinos and gravitational waves. They decoupled earlier, so they probe even younger epochs. Building those observatories is brutally hard, but progress continues. Expansion sets another boundary called the event horizon. Distant regions recede so fast their light never reaches us. Today's observable radius is about 46 billion light-years moving. That is not a distance you could ever travel. It simply marks where light had time to arrive. There is also a statistical ceiling called cosmic variance. We only have one sky to sample at huge scales. Fewer independent patches mean larger unavoidable fractional uncertainties. You can average noise down locally, but not there. Numbers help. The largest CMB modes keep percent-level uncertainties. No instrument beats that because statistics forbids it. What to remember: horizons and variance impose hard information walls. Step inside a cryogenic lab glowing blue with cold light. Black tubes and gold circuits nest around silent detectors. At the deepest level, measurement itself tugs on truth. Light arrives as quanta, and randomness rides along. Shot noise is built in, even with perfect optics. Read noise and dark current add their own chatter. Cooling reduces those, but never deletes the quantum floor. There is a bound called the standard quantum limit. It arises from uncertainty between conjugate properties of light. You can sometimes squeeze noise from one variable into another. Observatories exploit this, shaping fluctuations to favor the measurement. LIGO reduces noise several decibels using squeezed states of light. Astronomical spectrographs now explore squeezing for ultra-precise velocities. Thermal photons also swamp detectors in the mid-infrared. That is why JWST chills instruments near 40 Kelvin. Bolometers then count tiny energy packets with exquisite efficiency. Neutrinos barely interact, so you must watch huge volumes. IceCube uses about a cubic kilometer of Antarctic ice. It still records few candidate events on a typical day. Gravitational waves are even subtler at astronomical distances. Space interferometers will stretch baselines millions of kilometers for sensitivity. Every domain has a budget of noise and leakage. You can move costs around, but you cannot erase them. Net result: quantum randomness and hardware noise are ultimate roommates. We began with a wall you cannot photograph, even theoretically. Now you have seen what builds it piece by piece. Diffraction, atmosphere, backgrounds, dimming, crowding, scattering, horizons, and quantum noise. Each one can be bent but not completely broken. That is weirdly liberating because it tells us the game. We play for margins, stacking smart tricks against honest physics. Astronomers keep finding new margins, and that is the thrill. If this clicked for you, stay for more space clarity. I post deep dives that respect curiosity, not hype. One gentle ask: subscribe so you catch the next exploration. Thanks for watching. Under the same sky we measure together.